ahead and start the recording. All right. So, let's go ahead and talk about Ampere's Law. So, I had another session yesterday on Ampere's Law. If you want to check that out, you guys can feel free. It's in the session VODs. But let's go ahead and what exactly is Ampere's Law? One of you sort of give me your best interpretation of what Ampere's Law is. What is Ampere's Law?
Ampere's Law, not Gauss's Law, right?
Yeah, Ampere's Law.
That's the one with the charge enclosed.
Mm-hmm.
I don't really know in terms. I just know that it's charge enclosed over epsilon naught.
But that's Gauss's Law.
Oh, all right. Then it's u sub naught times the current, I think, maybe?
Mm-hmm. So we have some mu sub naught. Hold up. What is going on with my paint? There we go. So it's some sort of mu sub naught times a current. What current are we talking about? Also, welcome Jenny. Welcome Kevin.
Current enclosed?
Current enclosed, and that's equal to what?
The integral of the magnetic field times the distance.
The integral of B times some sort of dl, right? So,
Yes.
Essentially, this is what Ampere's Law is mathematically. What exactly does this mean? What are each of these working parts? What is this integral here? What is this B dot dl integral?
It's not the cross product, it's the dot product. So it's the angle between them, right?
What about the angle between them?
They should be parallel to each other. I don't know if this is right, but it's like Gauss's law is like the magnetic field changing over a certain distance, maybe, or
You're getting Ampere's and Gauss's law mixed up.
okay.
But so you're mentioning Gauss's law. What is Gauss's law? How do we use Gauss's law to find electric fields?
Oh, charge enclosed, right?
Mm-hmm. And so we have to. What sort of situations are we able to use Gauss's law in?
I don't know.
You can use Gauss's law for cylinders, planar situations, and spheres.
And what do all those have in common? Mohammed, you want to chime in?
I'm just guessing here, but like a radius and current enclosed.
Well, that's for Ampere's law, but what specifically are we able to use for Gauss's law?
Huh.
They're symmetric?
Symmetrical. That's the word I'm looking for. We're looking for some sort of symmetry. So for a sphere, imagine this is a sphere, 3 dimensions, you can draw a Gaussian surface, another enclosing sphere, that is always equidistant from the charge. And it's perfectly symmetrical. And then we can do the same thing for a cylinder, where we can have a cylinder coming along here, and we can draw another Gaussian cylinder around it, and it's cylindrically symmetrical. And then we also have planes. Now, why am I bringing this up? We haven't touched Gauss's law for almost a month now. I think maybe over a month. I sort of lose track of time sometimes.
A little bit of a question. Would the purpose of having symmetrical structures just be solely for the purpose of taking out a constant, which would be, across the surface, the constant would be, in Ampere's law's case, it would be like B.
Mm-hmm.
In Gauss's, it would be like electric field.
Exactly. Yeah. So for this class, obviously, this integral can be solved for literally any situation, even if it's not symmetrical, but it becomes a pain in the ass to actually solve. And in this class, we take these, mathematical equations, and we take a look at them and we apply them to specific situations symmetry where we can have a constant magnetic or electric field, and we can pull it out of the integral, and the integral is much easier to solve. So that's the whole point of why in this class we take a look at symmetrical situations. So if we're talking about Gauss's law and symmetrical situations where we can easily find the electric field, wouldn't it be the exact same thing for the magnetic field with Ampere's law? Also, welcome everyone that's hopping in here.
Yes, but can you do planar?
What was that? Can you repeat that?
Can you do planar for Ampere's law? Or
Why wouldn't you be able to?
oh, I guess you could. Yeah, you could.
Yeah, we'll actually have an example looking at that in a bit. But essentially, Ampere's law, if you have some sort of a symmetric, not charge, but in this case a current distribution, let's say we have a wire traveling along here, carrying a bunch of current, we can go ahead and, same thing where we would draw a Gaussian surface for Gauss's law, we'll sort of draw another, essentially a Gaussian surface around our symmetrical current distribution. And we can, because it's symmetrical, we know that the magnetic field is constant, and we can take it out of the integral, and it solves way easier. So that's sort of what Ampere's law is. It's very similar to Gauss's law from the electric fields, except it's essentially the Gauss's law for magnetic fields. And so what is this dl? What is dl in this case?
I always thought of it as the path, or I wouldn't say circumference or anything like that, but like the line surrounding surface of whatever Amperian surface you make.
I mean, that's exactly what it is. So, like, if we want to find our magnetic field, let's say here, our dl would be essentially, well, the dl is a line integral, but dl refers to the path around this circle on our Amperian or Gaussian surface. And you mentioned something about a circumference?
Right. In this situation, it would be a circumference, so it'd be like 2 pi r.
Yep, 2 pi r. And why do we know it's going to be 2 pi r? How do we solve this integral and get 2 pi r out of it?
Isn't it because you want to travel with the magnetic field, so it's got to be parallel with it, like the magnetic field will create an arc or a circle around that
Exactly.
pipe. So the distance traveled would be a circle around the pipe, because that is a constant magnetic field from that distance.
Yeah.
R.
Exactly. So we know magnetic field is constant along this path, and you mentioned that the magnetic field is parallel to the path we're taking. So what happens for a dot product when the magnetic field and dl are parallel?
It would be cosine 0, so it would be 1.
Exactly. It would just, the dot product essentially goes away. It's b times dl. And then we can take b out of the equation. Integral of dl is just our total length, which is our circumference. Boom. That's Ampere's law. It simplifies really neatly. And we'll also take a look at another example later on. We're actually going to take a look at an infinite sheet, a planar symmetry situation. And if you remember how to solve Gauss's law of planar symmetry, it'll be no problem. But let's go ahead and hop into an example. So we're going to have our infinitely long cylindrical wire here. It's going to be, has a radius a and a current density of j, uniform current density that runs out of the page. So we're actually going to essentially have a cross section of the wire here. And this current is coming out of the page. So what's going to be the total current carried through the wire? And then what's going to be the magnetic field when R is greater than A, so like out here? And what about when R is less than A, when we're actually inside? Let's take 5 minutes, then we'll talk about it. Also, if anyone hasn't already filled out the attendance sheet that's in the announcements, I would be greatly appreciated. I'll also put it in session text if anyone wants to find it there as well. All right, so let's go ahead and talk through this. So first off, what's the total current that's being carried through the wire if we're given our current density? How do you get the total current based on the current density? Go ahead, William.
Well, I know like charge density. If this is linear charge density, it's charge times length, right?
Mm-hmm.
So if this is current density, it would be current times length.
Is it a length or
Total area.
it's going to be an area? Because our current, this is an infinitely long wire going in and out of the page, and our current is traveling along it, right?
Right.
And our current's traveling along the entire length, but it's like sort of, it's current, it's the flow of charge. And what we're talking about is the total, J is our current density, it's the total amount of charge flowing through.
Oh, is it area because current can't travel through the conductor? It can only travel on the outside.
Well, this isn't necessarily a conductor, it's just a wire.
Okay.
I
just didn't know why it was area. But...
Yeah. But it's the total current that's flowing along here through this cross section of the wire. So
okay.
yeah, so as Mohammed said, we have to essentially multiply it by the area. And then also, fun fact, even if you didn't conceptually understand that, you could probably look at your formula sheet and think, oh, there's the letter J. It's the current over the total area. But so we have J is equal to I over A, so I is equal to the current density J times the area. What's the area of our cross section?
It would be pi a squared.
Yep, exactly. Yep, it's just the area of the circle, pi r squared. The radius r is a. So J pi a squared. That's our total current. So now, what would be the magnetic field outside of the wire? So when R is greater than A. How would we find our magnetic field outside the wire?
You just use Ampere's law, and then well, yeah, everything's in terms of J and A. So I mean.
So take me through the process.
Right. So we'd start with. Is the formula up at the top? We'd make our surface for that arbitrary R, which is greater than A. So it's outside
it's
of the,
going to look something like this. And I'm not going to.
Right.
Also comes around here, but don't want it to get in the way.
So we know that for that surface, dl, that we're still going to call it dl, that b would be constant, so you can take it out of the integral.
Yep, and dot product cosine of 0.
Right. Dot product, yep.
So we have b times the integral dl, which becomes what's the integral dl for our entire path?
would be pi r squared. Wait, no, not pi r squared. 2 pi r.
2 pi r. Yep. Exactly.
Yeah. Swapping the 2.
Yep. So there we've solved our integral, and we know it's equal to mu naught times I enclosed. So now we just solve for our magnetic field. So B is equal to mu naught I enclosed, which would be j pi a squared, but we don't need to write that again, over 2 pi r. Does this look familiar?
It's on the formula sheet.
Yeah, it looks familiar. I just don't know how you got that jump, but I understand it.
Yeah. What do you mean you don't understand how we made that jump?
When you do, I understand that you're doing the integral of b times dl, but what is that? Does that equal epsilon naught, or?
You're still thinking Gauss's law. No, the integral is equal to mu naught times I enclosed.
Oh, okay.
Yeah. Is it, you know how like for Gauss's law it was E dot dA is equal to Q enclosed over epsilon naught? That's essentially mu naught I enclosed is the Ampere's law equivalent of Q enclosed over epsilon naught.
Yeah, that's how you got I and epsilon naught. Okay. Yeah. I was just confused how you got that.
But yeah, this looks familiar. This is actually on our formula sheet, and that's for any symmetrical current distribution for a wire, obviously, for a cylindrical symmetry. It's the same thing with Gauss's law, where essentially we can go ahead and solve our integral and take 2 minutes to do it, or we can just know E is equal to K times Q enclosed over R squared. The same thing for our Ampere's law simplified form. It's mu naught I enclosed over 2 pi r. Right?
But that's only for if r is greater than a.
Well, for r is greater than a, because our enclosed charge is a constant no matter where we are, as long as r is greater than a, right? This is mu naught times j pi a squared, so mu naught j pi cancels out, a squared over 2r. That's for any radius r outside of a. So now what about when r is less than a? How do we find the magnetic field inside the wire?
We could start with a new surface, just to illustrate that the surface would be inside the wire.
So something like that.
And then you'd find, basically follow the same steps. You'd find the integral of dl, which would be, in the same scenario, it would just be 2 pi r times b.
Yep. So what's different about inside the wire versus outside the wire?
Right, the enclosed current.
The enclosed current.
It would be, less.
Yeah, so when we're outside the wire, our enclosed current, is a constant. It's just j pi a squared. Because it doesn't matter where we go, the entire wire is still enclosed. In this case, when we're with r is less than a, if we change what r is, if we move out to here or into here, the total enclosed current changes. So we can try to find our total enclosed current as a function of the radius, right? How do we do that?
Does r just become a?
So what do you mean?
Like that the bottom radius is going to be a, and the charge enclosed is also going to have a radius of a. So everything is going to be in terms of a, the distance from.
not quite following what you mean.
That's okay.
Yeah, because I think you sort of, I think you might have the right idea, but I'm not sure if you're really quite putting it into words. But so what do you mean about R becomes A or A becomes R and whatnot?
So the radius is less than A.
Mhm.
So the cross section of what you're looking for the charge, like you're looking for the current that goes through A, and then also you're looking for the magnetic field in A. Beforehand, like the radius was bigger than R, so the current that is enclosed, that radius is A, but the magnetic field, that radius is in terms of R. But when that's as well as I can explain it, I guess.
Yeah. So basically, our enclosed cross section changes as a function of R. So how do we get our current based on what we're given?
We know that the the current density is the same, throughout the surface. So we can use the same J to calculate the I enclosed for the smaller, cross sectional area.
Exactly.
So it would be in terms of R, like he was saying. It would be J pi R squared.
Exactly. Boom. We have our charge current density, J. The same thing, it's J times our cross-sectional area. In this case, our cross-sectional area, instead of being the entire wire, pi A squared, it's just our smaller pi R squared. J pi R squared. And then, it's just the exact same thing. We just take this enclosed current, and we plug it into our simplified Ampere's law.
Dang it! I meant R. I said A. I meant R.
I'm pretty sure I knew what you were talking about, Leonard, but you kept on mixing things up, and I wanted to make sure that. But yeah, so we just go ahead and take this. B is equal to mu naught I enclosed, which is J pi R squared. We have pi R on the bottom, so it ends up becoming mu naught J. Pi cancels out from the bottom. 1R cancels out from the bottom. Mu naught JR over 2. So our magnetic field actually sort of increases as a function of R. It looks something like this, and then dies off as a function of 1 over R.
Right. I like that part right there, like the kind of calculus of that circle. I don't quite get, because like,
what do you mean the calculus?
So for that graph right there, like the x-plane would be like as R increases.
Yeah.
So
So this would be our magnetic field, and this would be our radius R.
And I know that the middle is right at the edge of the wire.
Yep. So that would be
like A, yeah.
at A. So what don't you understand about this?
I mean, I don't know. I mean, maybe I just don't get circles, but I just didn't think the line would be straight. That's what I'm saying.
Yeah, I mean, why? I mean, it really doesn't seem to make sense. Like, nothing in this class necessarily really makes conceptual sense when you first look at it.
Yeah.
But we did the math, right? The math checks out.
That's true.
We have our enclosed current, which is a function of R squared, and we divide it by our 2 pi R. So we have R squared on the top and 1 R on the bottom, so it becomes a function of R, increasing as we go out. Because as we go further out the circle, let's say we have a circle here, and we go from 0 radius out to just here.
Right.
We just get this tiny little increase in radius. Instead, if we increase the same distance, but we're all the way out here, instead of this tiny little area, we have this entire ring of cross section that ends up increasing. So as we go further out in our wire's cross section, each incremental increase in radius equals increasing amounts of surface area added, which means increasing amounts of enclosed current.
All right, I think I get it. Right. So the equation B equals U naught JR over 2. I was still thinking that, like, on the right side, R would be like R squared, but the two R's cancel out, like, in that way. So, yeah, it would be like linear instead of like quadratic, like I was thinking. So, yeah, I think that sorts itself out.
William, you want to say something?
No, I was just gonna say it is surprising that it's a linear increase and an exponential decrease. So.
Yep, it's the same thing as we looked at with Gauss's law, right? For if we're inside an insulating sphere of charge, where it would increase linearly as a function of the radius, and then once we got to the edge, it would then die away as a function of, in this case, for a sphere, it would have been 1 over r squared. But yeah. Does anyone else have any questions about this?
Nope, we can move on to the next
All
one.
right.
I know it's loads of fun.
Loads of fun. Yeah. So now we're going to go ahead and take a look at an example where instead of having a uniform current density J, we're instead going to have a non-uniform current density. So we're going to have a current density J is equal to B R squared. B is a constant. Essentially, the further out we go from the center, the more current there is per unit area. So let me go ahead and draw a new wire cross section. It's also coming out of the page. Oh, and by the way, if our current is coming out of the page for this example, what direction is our magnetic field in? How do we find the direction of our magnetic field?
Counterclockwise. Right hand roll, thumb in direction of current, and then curl your fingers.
So what direction did you say it was in?
You said it was out of the screen, right?
Yep.
So your thumb points out of the page. So you curl your hands
Would be counterclockwise.
counterclockwise.
Mm-hmm. I guess you said, did you say counterclockwise at first, William?
I thought I did.
Okay, your mic might not have picked it up. It sounded like you said clockwise. I was trying to catch you with your pants down there. Yeah, it's counterclockwise. Point your thumb out of the page, rotate your fingers around. So now I'm going to have our non-uniform current density, J is equal to BR squared. So now it's going to be a bit trickier, but we want to go ahead and do the same thing. Find the total current carried through the wire, find what the magnetic field would be at when R is greater than A, and then also when R is less than A. Let's take 10 minutes and we'll talk about it. Might need a little bit of calculus for this one. All right, so how would we actually go ahead and find our total current flowing through the wire based on a non-uniform current density?
You just use the same equation that we used earlier, which is J equals I over A. Make it I equals JA. And we know that J is what, BA squared, and
Are we
that
able,
A
is
IA squared.
are we able to do that? Because that would be the case for a uniform current density. How do we find it if the current density changes as a function of R? We have to use a little bit of calculus here to do this. let's put it this way. The formula that you guys are given here, j is equal to I over a, so we'll say I is equal to j times a, is actually a simplified version of the actual formula that you use for when j is a constant. Essentially, we have to integrate our j over the entire area that we're given. So in reality, it's actually I is equal to the integral of j times dA. Where if j is a constant, it comes out. Integral of dA just gives us our area. I is equal to j times a. That's what we had before. But in this case, j isn't a constant, so we can't actually pull it out of the integral. So how would we actually solve this? Well, first of all, go ahead, William.
No, I don't have anything. I was just gonna say, you said that j is not a constant.
It's a function of the radius, right?
Yeah.
So it's actually, I can write this as j of r.
Yeah. I would agree, because like the area is not symmetrical. J
Well,
is not constant.
well, the area is still symmetrical. The j is still symmetrical. It's just it's not a constant, so we can't take it out of this. Because if we're integrating over dA, it's our area actually is also a function of the radius, right?
Yeah, okay, I see what you're saying. It's a non-uniform density, so j is not constant.
Mm-hmm. So how do we actually integrate over dA? There's two ways we can do this. First of all, what is the area of a circle in terms of the radius?
Pi r squared.
Yep, a is equal to pi r squared. So then if we actually take the derivative of this, dA, what would dA be?
2 pi r.
2 pi r times what?
No, that's the
Well, in this case, it would be
dA.
dA dr would be 2 pi r.
Yep.
So we can go ahead and move our dr over here.
Oh yeah, you're differentiating with respect to r.
Yeah, exactly. So we have dA is equal to 2 pi r dr. We can go ahead and plug this in here. So this is equal to integral of br squared, that's our j, times 2 pi r dr. Right? We can go ahead and take our constants out. We have 2 pi b, the integral of r cubed dr. You guys know how to solve that, right? What's the integral of 1 over r cubed? Sorry, what's the integral of r cubed?
R to the n plus 1 over n minus 1? No.
You were close there.
R to the n plus 1 over n plus 1?
Yep, exactly. It's just 1/4 r to the 4th. Equal to 2 pi b, so we'll have pi b over 2, the 2 and the 1/4 cancel out. And then we have r to the 4th. Now, what are we integrating? What are our bounds of our integral?
You want to go from out to in, right?
So what are our bounds? Let's say 1, we're going to start at...
I was going to say infinity to 0, kind of like that you do in the other law. Gauss's law.
From 0 to infinity. But does our wire go all the way out to infinity?
No, so just go with R.
It goes out to the outer radius, which in this case is A.
A.
So that just becomes pi b a to the 4th over 2. That's our total current. There's another way we could have done this. How else could we have done this? Is anyone familiar with polar coordinates? I'll give you a hint. It ends up giving the same thing. But essentially, polar coordinates, what's dA in terms of polar coordinates? So like for Cartesian coordinates, dA is equal to dx dy. Right? And then a dz as well, but in this case dA, or it could be dy dz or dx dz. But in this case, we'll just say it's dx dy. For polar coordinates, what does it end up being?
X and Y.
Hmm?
X and Y coordinates.
Well, this is for x and y coordinates, or Cartesian coordinates.
Mm.
What about polar coordinates? You guys might not have had. You might have only seen this once or twice so far, so don't blame me if you guys haven't, like put it to memory. I think
Is it the ones like I, J, and K?
That's still like
That's not it.
that's still like Cartesian coordinates, or
Would it be like the full 2 pi and then, well, not 2 pi. Well, yeah, 2 pi and then A? Or is that wrong?
no, not quite. It ends up being, so polar coordinates, right? Instead of x and y, it's a function. It's r and theta, right? And dx dy, if we transfer this into polar coordinates, it ends up becoming r times dr times d theta. And then the integral of d theta from 0 to 2 pi ends up being our 2 pi that we get right here. And then it's the same thing. We have this r dr. Fun fact. But it doesn't matter too much. So now that we found our total current, how do we go ahead and find our magnetic field when r is greater than a? Come on, what's our magnetic field as a function of the enclosed current?
B equals epsilon naught times I enclosed over 2 pi r.
Yeah, or mu naught, but I know what you mean. Yep. Mu naught times I enclosed over 2 pi r. What's our enclosed current? Well, when r is greater than a, it's a constant. It's just this. So pi cancels out, so we have mu naught b a to the 4th over 2r. Right, nice and easy. So now, how do we actually go ahead and find our magnetic field inside the wire when r is less than a? How do we find our enclosed current? Wouldn't it be the same process as we had here?
Yeah, you just substitute A for R.
Exactly. So instead of instead of integrating from 0 to A, we're just going to integrate from 0 to our arbitrary radius r. So I enclosed just becomes pi b r to the 4th over 2. And then we plug it into mu naught I enclosed over 2 pi r. We get b is equal to mu naught, pi cancels out, b r to the 4th on top, 1 r on the bottom. We have r cubed, mu naught b, r cubed. Oh, I just realized we actually have a 4r right here. Because we have 2 pi r here and we have our over 2 here. Mu naught b r cubed over 2 times 2r. So we have over 4. Mu naught b r cubed over 4. Does that make sense? Anyone have any questions about this? So Kevin, give me a run through of this entire process again. What did we actually do to find our enclosed current?
The enclosed current would be, it would be, instead of, well, because it's not constant, you can't use I over A. So, referring back to like, I being equal to the integral of the current density and with respect to the area, I think.
Mm-hmm.
You would then plug in J, that's defined as like B r squared, and
Yep.
dA would be well, the derivative of dA would be 2 pi r dr.
Yep, exactly.
Then you would take the constants out and integrate r cubed dr.
Mm-hmm. Just gives us r to the 4th.
Right.
And then the 1/4 comes through.
Mhm.
Exactly. And then we just take our enclosed current and we plug it into our simplified Ampere's law, mu naught I enclosed over 2 pi r.
Right.
Boom.
So we're just following the regular steps after,
Exactly.
you know, the calculus and whatnot.
Exactly. So,
And then for the situation where there's where r is less than a, it would just be subbing in r for the enclosed current.
yep, exactly. And then we have to actually, the r actually ends up coming through, and it actually becomes a function of r cubed as we increase. So if we actually were to go ahead and plot our current, our magnetic field as a function of r, it's going to look like some sort of increase like this, and then a slow 1 over r decrease.
I have a quick question. What is BR squared again? Just real quick.
Br squared is our current density. So
Oh, okay.
B is just a constant. It's arbitrary. And so essentially what this means is as we go further out from the center, the amount of current coming through each, infinitesimally small bit of area increases. So like at the center, there is 0 current versus before we actually had a constant current throughout the entire thing. For here, there's 0 current at the center and it increases as we go out.
Is that true for all? I just saw that it read says a non-uniform current density.
Yeah, for any direction we go in.
It starts at 0 and gets All right, exponentially bigger. Okay.
Yeah, not exponentially, but I know what you mean.
Yeah. Okay.
Not technically exponentially, but yeah, it increases.
It increases. Gotcha.
So, you guys don't have any other questions about this? Essentially, all you need to do for this problem was recognize that because it's non-uniform, we have to actually integrate over the area. And then apart from that, it's the exact same process as before, just using different enclosed charges. So, let's go ahead and hop into one last example. So far we've just taken a look at cylindrical symmetry. There's no spherical symmetry for currents, by the way, if you guys were wondering. It's just cylindrical. And now let's go ahead and take a look at a planar symmetry situation. So we're going to have an infinite sheet of currents, n wires per unit length. So it's going to look something like this. If this is our infinite sheet of currents, we have a bunch of little wires along here like this. And there's n wires per unit length. And they're carrying current into the page. So how would we actually go ahead and find our magnetic field at any point along here, along our x-axis? Let's take about 5-6 minutes, then we'll talk about it. Give you a hint, you're going to need to actually go ahead and take a look at our original unsimplified Ampere's law. That's where I'd recommend starting from. All right, so how do we actually go ahead and find our magnetic field based on this infinite sheet of current? How do we actually go ahead and find our magnetic field? First off, let's start with Ampere's law. We have our dot product B dot dl is equal to mu naught I enclosed, right? What do we do from here? Say we want.
Next would be the Amperian surface.
Mm-hmm. So what's that going to look like? Let's say we want to find it right here. What is our Amperian integral path going to look like? Let's say, first of all, we're going to want some sort of a path along the spot where we actually want to find the magnetic field for, right? Have a little bit along here. You guys remember back to...
Right. You'd make a rectangle, sorry.
It's a rectangle, yeah. So, why is it a rectangle? Why are we doing this?
Being able to find the enclosed charge, it would be limited to the height of the rectangle.
Yep. So let's call the height h. So h. So what's our total enclosed current?
Can you just like label it like I, or is there a certain?
What would it be as a function of h, I naught, and our n wires per unit length?
Well, it's definitely gonna be in terms of H.
Mm-hmm. So if we have n wires per unit length, what's our total length that's inside our loop?
H.
H, exactly. and then we multiply by the current per each wire.
Oh yes.
So it's mu naught n h I naught, where I naught is the current in each
Flux,
wire.
right?
Go ahead.
That's the flux, right?
Well, the equivalent of what our flux would be.
Yes.
Yeah.
Yeah.
So now, how do we actually go ahead and solve our total line integral? We want to integrate over each of these, over this entire loop, right? Want to integrate here, through here, and also through here. There's two of them where our integral actually ends up being 0. Which two? Let's say 1, 2, 3, 4. Two of them are b.dl integral is 0. And why?
4 and 2, because if this is pointing into the screen, then it's rotating clockwise, like magnetic fields are clockwise. So, at for an infinite sheet of charge, I just know that the magnetic field lines are going to point down or down, because the x components actually cancel out. You can use separate. You'd have to draw it out, the magnetic field lines, but you can. I don't know how to describe that, but
yeah. So essentially, for each of these little wires, we have a bit of magnetic field that goes like this. For each of them, for each individual part, and we actually find that all the components in the x direction end up canceling out, and so on the right side we have all these parts going like this, so we have our net component in the y direction going down, and on the left side we have all these different parts that are canceling out, and we actually have a net magnetic field going upward. So because the magnetic field is up/down, why does our integral go away for part 2 and 4?
There's a dot product between the invariant surface, which would be like the side of H, and then it would be the dot product between that and the magnetic field.
Yep.
So that would cancel out to be 0.
Yeah, exactly. Or, well, in this case, the dot. What's the dot product simplified to?
angle between them.
Yep. What about it?
Well, cosine.
Cosine. And what is this angle between DL and the magnetic field for 2 and 4?
That cosine of 90.
90.
Yeah, it's 0.
Cosine of 90 is 0. Exactly. It disappears. So now, what about part 1? Let's say we're doing our integral clockwise. So we're going down here, 0 for 2 and 4, and we're going up here. So what is our b.dl integral for part 1 here? What does that end up becoming? Is b a constant over this whole stretch?
Yes.
So b can end up coming out. So it's a b times the integral of dl. So hold on, let me just write this down here. So we have our mu naught nh I naught is equal to our two integrals for 1 and 3. For part 1, b comes out. So it's a b times the integral of dl. What's the integral of dl?
That would be h.
Yeah, exactly. It's just the length h. So it's bh for the first one. And now for part 3, b, once again, is a constant, so it comes out of the integral. What's the integral of dl? It's the same thing, right? It's just h again. It's the same height.
Yeah, I was just gonna say L, but yeah, H.
Yep, exactly. So we have our mu naught n h I naught is equal to 2bh. And now we just solve for b. So b is equal to 2bh. H actually ends up canceling out from both sides. So it's mu naught n I naught over 2. Boom. Nice and easy. It actually ends up, h ends up canceling out, and so it doesn't matter what we define our h is or whatnot. An infinite sheet is always going to give a magnetic field of mu naught n I naught over 2. So that means our magnetic field is actually constant, right? It's not a function of the distance away.
Where did you get the first BH again?
The first BH was for part 1. The second BH is for part 3.
Got it. Yep. Same. It would be the same. Right?
Yeah, exactly. Because our magnetic field is traveling down, so in the direction of the integral, and then up, once again, also in the direction of the integral. Nope. You're not ni over 2. So it's actually independent of the distance. It's just like an infinite sheet of charge, right? Remember how it was sigma over 2 epsilon naught? Where it's actually independent of the distance. And it's actually, this is what's given here in your formula sheet. Half mu naught n I. Anyone have any questions about this?
Nope. I'm good.
All right. Well, in that case, that's going to be the end of the session. Hopefully this helped you out a little bit. If anyone wants to go back and check out yesterday's session, they can. It's in session VODs, and then the session is also going to be uploaded there if you guys want to check it out again later. If you haven't already, if you could fill out the attendance form that's in announcements or session text, that would be greatly appreciated. Thank you. And have a good day, guys. Good luck on your quizzes tomorrow.
Thank you, Dylan.
Thanks.
Thank you.